テスト。
So this is just so the recording picks up, right? This isn't
live streaming.
Okay, yeah. So
Recording.
yeah. I guess what I mean is I should use it even if it seems like I can be heard by the room. I should use this even if people can hear me because yeah.
This is very professional.
Is it? Is that better? Is the
You want to be in the video?
I guess that's probably people will feel better about that.
Yeah. Oh yeah. But, that's fine. Yeah, that's perfect.
Okay. Hello. Yeah, this is the machine.
Oh, it looks like is it broadcasting already?
Yeah, I think so.
Oh, okay. So people are the 5 people watching now.
Well, probably 2 of them are us.
People
Oh boy.
I think it's better with otherwise people
Shaded. Yeah.
maybe for the recording group, like if someone asks you a question, maybe.
I have to repeat it.
Yeah.
Do you want to kick it off, or do you want to announce, like, describe what Consciousness Club is and things like that?
Oh, okay.
Since a lot of the people on the live stream have no idea what's what's up with the event. Sure.
No, just
Yeah.
introduce. Okay, should we stand here?
Yeah.
Okay, so yeah, just for those who are not familiar with this event, we are organizing so-called Consciousness Club weekly, and we usually discuss like various topics, including like neuroscience, AI, physics, information theory, philosophy, like anything related, anything that's interesting, like anything that helps us understand consciousness or create consciousness, or maybe like even if you're not interested in consciousness, that's also fine. So today like we have Nicholas Guttenberg from Araya, and he will talk about what he has been working on with Olaf, who's from White House. That's another interesting research institute based in New York. And yeah, so Nicholas is going to talk about learning to communicate. Okay, Nicholas.
Thank you. These things usually go for about 2 hours, and the talk isn't really supposed to be filling the entire time, which means that in general, please interrupt, ask questions Otherwise, we'll be out of here in 30 minutes. So this is stuff that Olaf and I were interested in seeing how neural networks would actually go about creating language and what sorts of interactions they would have if they were communicating with each other. And there's a lot of sort of things that we just did to see what would happen. This talk is sort of trying to sum up all of that and actually take the core of it that could actually be extended into some new research, since a lot of it otherwise is just a kind of just so story. So the focus that we've kind of come to is that the interesting thing about communicating is that the listener has to actually integrate what they hear into their own understanding. And so that kind of suggests a learning algorithm in a way, a different learning algorithm than the way that you would train a neural network to begin with. So if I think about different kinds of learning in a broad sense, learning systems improve with time, and improvement is very vague here. It could be improvement with respect to a specific goal, or it could be some alignment of what they do with to be correlated with something in their environment. But the over time thing is kind of important to distinguish learning systems from systems which just start with a successful strategy. And what that means is that they both have to somehow internalize information that they didn't have before, usually coming from the environment. And they have to keep that information and propagate it forward in time in a way that between the two of them, between those two factors, they're able to actually improve on whatever it is that they're being evaluated on. So there's a lot of different ways that you can do that. The most common way to keep information propagating forward in time is just don't do anything to it. So if you just keep that information in a memory and don't change it, then it is propagating forward in time pretty freely. But actually, the propagation mechanism can itself have a lot to do with the way that the information is gained. Since there's usually a lot of information and only a small amount of it is relevant to that agent's performance. So in evolutionary learning, you actually induce the flow of information into the system by having some of the information not propagate forward in time. You have some population and the members of the population reproduce, but some of those offspring die. The ones that die versus the ones that don't are transmitting, are basically a signal, a feedback signal, and that signal gets internalized when it's kind of juxtaposed with the mutation or with the noise. So death is actually information gain, and then replication is the propagation forward. In inferential learning, you can just sample, and you just keep a record of all of the samples, everything that you've had before. Keeping that record is the forward propagation, no big deal. But then the way in which you integrate new evidence to the prior belief about the system, you need something like Bayesian updates or whatever in order to do it in a way that's stable, so that you don't just run off somewhere or get worse. So the kind of ability to converge there is something that needs a bit more care. And then in optimization, what you do is you may not have this kind of branching population, but you have one point, and the information is injected into the system by the direction in which the point goes next. Whereas the fact that the point is not just jumping around randomly is the propagation forward in time. So all of these kind of are different takes on the same sense of a system which improves over time. So we can ask, well, what else can we design? If I have something like communication going on, when I have a lot of agents and they're sharing messages, and in fact I have a pool of messages that outlive the agent potentially if the messages are being retransmitted by people who hear them, in that case those messages provide a new mechanism for keeping the information around. And then the thing we need is a way to take that pool of messages and integrate it with the new information flowing in, such that the result is actually improving rather than just random walking around or things like that. In evolutionary systems, this has a massive effect. If you have horizontal gene transfer, then instead of losing all of the information of a branch that goes extinct, you actually can keep all of those X's, all of those information gains along the main branch while still actually receiving feedback about more sort of macro structures of the population. And what that ends up meaning is that instead of taking thousands of years for bacteria to become immune to antibiotics, they can become immune in 60 years or 6 months even, just by sharing that information across the pools that didn't die. So this is something that would potentially make a big difference. There's another thing about communication, which is that you can't say everything. So if you have some agent that has a lifetime of experiences, sending messages is part of that lifetime of experiences. It's only going to be able to spend some small fraction of its total time sending messages about what it's actually experiencing. So it has to be selective. It has to actually compress what it wants to communicate about to be relevant in some specific way. And that means that if you're just transmitting data and there's a lot of redundancy, that's not going to be very efficient with communication. If you move past that and actually transmit what the data means, then you can actually squeeze the messages down to a much smaller fraction. And so there's kind of a hope that if we look at the kinds of learning that emerge with communication and with networks that communicate with each other, that specific kind of bottleneck would encourage the formation of sort of representations of knowledge rather than representations of data. So it's a pretty common thing to build things like autoencoders, which take some individual piece of data, represent it in a compressed way, and then try to reconstruct it. And in that kind of compressed representation, it gets something fundamental about the manifold on which that data lives. It gets sort of abstraction over it and commonalities. In this case, we're taking a step back and we're doing that to the space of tasks. So we want to ask, out of all of the things that you could want to do, what are the commonalities? How do you actually talk about things that could be done or things to do, what you should do, things like that. And so with this, with these setups where we're going to get these networks to communicate with each other, by looking at the latent representations or the messages that they send, we might be able to understand some underlying patterns behind the space of tasks that we ask them to do. So that's kind of a hope. It's not a guarantee. It may not turn out the way exactly we want, but it's a suggestion that something interesting should happen. So the other thing about this is, as I said, when you communicate, there has to be some way to take those messages that you receive that summarize something about the task or the data, and then integrate them into what has gone before. If you have your own experiences and then someone sends you a message, you have to take the message and your experiences, put them together in a way that the result doesn't too heavily weight one or the other, so that you actually improve on the whole from receiving those messages. So in a way, this update rule that lets you pull in a message into your brain state and use that to make better decisions in the future, that's a learning algorithm. And the pool of messages represents the parameters in a way, the set of learned knowledge that the society that you're simulating has managed to extract out of its environment. So if we look at long-term improvement specifically, then I'm going to say by teaching agents to communicate, we're also teaching them to invent a new learning algorithm, something other than gradient descent. We don't have too much control over the form that this learning algorithm takes, but the nice thing is that it could have properties that are more similar to how humans do symbolic reasoning, in the sense that you might not need huge amounts of data now to actually improve on a given task. Since you're going to be taking a small set of messages and using them to actually determine what you do, as opposed to iterating and kind of annealing over hundreds of thousands of repeats on the same set of data. And also by setting up the exact way in which the network is allowed to try to do this, we can control the properties of the learning algorithm we want it to make. Okay, I just have to caveat saying, just because I'm saying that there's a kind of communication which should be equivalent to learning, it doesn't mean that all communication is equivalent to learning. And this is why when we set this up, we have to be careful in choosing the task. In order for this to work, the communication has to be about long-term improvement. If it's just something short-term, like coordination games or things like that, where the meaning of the message becomes irrelevant after a short period of time, those networks will not develop a learning algorithm. They'll just develop some kind of coordination game playing algorithm, but they'll forget. They won't carry information forward. Another situation is that communication can be used to actually generate information between agents rather than transmit information that they've received about their environment. For instance, making some kind of negotiation or agreement, or collaborating to produce some kind of content. And that sort of information generation thing is interesting, but I don't know if that's what we focus on. I'm actually, at the end of the talk, I'm going to talk about computation and how that relates. And that probably is most similar to communication to generate rather than communication to transmit. It's not necessarily the case that we're still in the space of learning algorithms at that point, but we are in some other kind of space of function, which might be interesting to investigate. And the other thing is that not all communication is about improvement. So there are things where there may be some adversarial setup and communication is done to deceive or manipulate the other agent. There's things where communication provides just a sort of a social signal, which is unrelated to the actual performance of the one who communicates to the one receiving it, but is somehow stabilizing an overall situation, things like that. And that's also not necessarily going to give you a straightforward learning algorithm. But all of those are meaningful kinds of communication that exist, and actually you could use these same techniques to explore. So, okay, so we need something that has the possibility that improvement continues to happen. If it's just a one-shot thing, that's going to kind of limit the stability that we get the network to develop. If the network only has to send one message in its lifetime, receive the message and use it, it won't actually learn some kind of inductive process, which allows it to take sequential messages or sequential evidence and gradually improve over time. And we really want that kind of inductive structure so that it generalizes to things more than just what we train it on. And the other thing which is kind of tricky is that we're going to be training these things with gradient descent. So if we picked one task and trained them to communicate, to solve that task, they might communicate at first, but then eventually they would just memorize that task. So we want to operate in a regime in which there's still some kind of uncertainty in the system when it comes to test time. There's some source of entropy left that you can't just train away with gradient descent. That's maybe a bit of a long-winded way to say we don't want to overfit. But the problem is that in a lot of these communication cases, especially if we're talking about agents that share information about themselves, they can kind of tune themselves to fit into a known distribution, which then they can just assume rather than actually having to talk with the other guy to find out. And that is maybe a more subtle point that we're going to have to watch out for. So what we're going to do for this is we're going to look at metalearning. And in metalearning, what you do is you take something that a learning algorithm would normally be used for start to finish, and that's just one data point now. So normally a learning algorithm receives a number of data points, and then by seeing all of those data points, it converges towards some kind of behavior. We just want to say, okay, data set behavior. And then each data set behavior pair is now a data point in some bigger task, a task over the space of tasks. So if we train on that, the selection of that subtask is the sort of residual entropy that the gradient descent can't just memorize away. So normally you take multiple data points and learn a classifier. In this meta version, you're learning a function that maps you from data sets to classifiers with one network that operates on all of those tasks. So you need a large ensemble of tasks. That's a bit annoying. Real world data would be best, but then you're kind of looking at the situation that you need maybe 10,000 tasks, 100,000 tasks would be nice. It's easy to find things with hundreds of tasks or even maybe 1,000 tasks in image tags or something like that. But it's a lot more convenient since we're playing around with these algorithms to start with and we don't know what's going to work or not to actually just generate our tasks. So what we do, for example, is to take a pair of Gaussians, parameterize their separation, their covariance matrix, and just randomly vary those things. So now we'll learn an algorithm that generates classifiers that classify between two Gaussians. And of course, we could do 3 Gaussians or 4 Gaussians. We could do weird distorted functions instead. That's all fairly easy to generalize. So just to start, before we even talk about communication, what do we need in order to put data sets into a network rather than data points? One of the things is that if I change the order of the data, it should still mean the same thing towards the classifier that I build. So even if I use something like a recurrent neural network to read the data points in one at a time, I don't actually have that invariance. It'll more strongly care about the recent data compared to the older data. What I can do, however, is I can use the idea of pooling. So a pooling operation takes a bunch of elements and then somehow either addition or multiplication or any kind of element-wise reduction procedure such that the result of that ends up being independent of the order of the inputs. So you can, for instance, add together a bunch of numbers and then it doesn't matter if you exchange numbers in that sequence, or multiply a bunch of numbers, take the maximum of a bunch of numbers. All of those procedures are invariant to the input and reduce a set of inputs down to a single output. So as long as I wrap everything I do in pooling, then the result will eventually be invariant to permutation. But the problem is if I just do everything and then pool, I'm going to have very low order sorts of things like I can talk about the average of the data set, but I can't talk about the standard deviation of the data set. So what I actually want to do is I want to transform my input data, do some pooling, combine it back with the input data, transform it, do some pooling, combine it back with the input data, transform it, do some pooling. So then every time I do pooling, I'm taking an average, but I'm taking an average relative to all of those prior averages with some arbitrary nonlinear function, mixing things together. And that gives me a much richer space of models that I can build easily. So after pooling, that pooled output is in some sense a representation of the information that was in the set of data that the network had as input. It's a representation of the task. And I can take that task representation, attach it to individual points from the test set, and then run that through a standard dense network to get classifications. So it's sort of like saying, I want to do the classification of this test data conditioned on this data set. So in a normal,
I don't understand how you say data point. You don't take data points, you say data sets. And then you say, and then each data set is a task. Of corresponds to a task.
Yeah.
Can you say how this works out?
So like each of these squares could be seen as being as a different task, right? So in this case, I want to get some new point, which I don't know whether it's red or blue. And based on where it is in the plane, I want to say, is it likely to be red or is it likely to be blue? So what I should do in each case is defined by the data where I do know whether it's red or blue, right? If I know all of these points and I see a new point, I should make one kind of conclusion. But if I saw these points instead, I should make a different conclusion about this new point. So normally what I would do is I would say, I'm learning a model that gives me, say, a probability of the class conditioned on the coordinate of the point that I'm asking about. And then that model has parameters, which I learned through gradient descent to optimize something, some expectation over these points, right? In this case, what I'm going to do is I'm going to take all of these things and I'm going to optimize an expectation over all of these of a probability of the class given both the test point, that is some unseen coordinate, and given all of these coordinates and labels. And the whole data set.
So the learning, the training set.
Yeah, the training set. Yeah. Yeah, and the issue is that, for instance, I may have a different number of points each time, or I may change the order and things like that. So I need to somehow collapse that down into some latent representation. So I can just do P of Y given X and Z, where now Z is some complicated function of all of this that simplifies it to make that learnable. For all of these points, for that point set. Yeah, it's a latent representation of different data sets. Sorry, I probably should have been repeating the questions. What should we do? Okay. Okay.
Maybe write down the difference between P of.
Okay, so Martin wants me to write down the difference between the two conditional probabilities.
So
I have some set of X and label, and I have some XT, and I want P of Y given that. Where T is the test point. Yeah. As opposed to this.
me, this is very clear.
Okay.
I didn't. Yeah, okay.
All right.
I don't know, maybe you could say it in a more intuitive way, how you can switch basically between tasks, or an example, I don't know, or funnel. But essentially that you are solving this specific problem, but if you want to solve this other specific problem, that's the equivalent of switching.
I think you're going to have to repeat what you just said.
Yeah, great. Well, I don't know. You could repeat it, so. I don't know. It's just well, that's awkward. What did I just say? No, I don't know. Like just maybe maybe this is simple to you, but yeah, you can see this as solving different problems, and you have to mind switch between those different sets of problems, right? And this is what we are doing right here. So not only where each problem is represented by a data set.
so given a precondition on a set of problems, then if you feed that to yourself, you kind of separate the problem of solving a problem and the problem of choosing first what to solve and then solving that problem. Does that make it easier? Maybe not. Okay.
I let you.
I mean, another way to think about this is if you think about the difference between sort of parametric statistics and non-parametric statistics, that because I'm giving this an ensemble of tasks, I'm non-parametrically learning the sort of space of models on which to do parametric statistics. So normally I would have to come in with a model and say, these are my parameters. I want to do likelihood estimates of these parameters, or I want to do gradient descent on these parameters or whatnot. But I'd come in with that model, and that model would be based on my understanding of what the possibilities are. In this case, the network is learning what the possibilities are. And the latent representation is essentially the parameters that parameterize a given model out of that space of models. So then when given a specific data set, the network is using that data set as evidence to infer the parameters in the space of models that it itself constructed. So the gradient descent is constructing the space of models, but then the forward pass is just doing inference on the parameters. Okay. So this is what happens. I've been wanting to put this slide up because I think this is a lot easier. If I give it different data sets, oh, the contrast is really bad on that. Okay, so you probably can't see it. There are blue points here, 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 here. So it actually, with this 2 Gaussian data set, you can actually get fairly complicated decision surfaces because the Gaussians can intersect and the covariance matrices can make them go off in different directions. So they actually, the classifier has to use that covariance to figure out what class a point should belong to, not just the vector separating the centers of the 2 Gaussians. But in this case, in each of these frames, the network calculates the classification as just a forward pass. There's no additional gradient descent, no additional kind of iteration or learning going on. It's just a function that outputs a classifier given data. And on at least these very low dimensional cases, like these 2D, 2 Gaussian cases, this is actually a really effective thing to do, especially for very small data. Normally with parametric versus non-parametric statistics, the problem with non-parametric stuff is you need a ton of data to feed it. Here, it's kind of a compromise solution. The network has learned that the world looks like pairs of Gaussians. And so it doesn't actually need to relearn that whenever it's shown the data. It doesn't need to figure out like classification space is mostly contiguous, or I don't have weird sine wave kind of distortions of this or anything like that. It only needs to fit the parameters that actually vary in the set of tasks.
So it has to find out, just to find out which task it was and then justify it.
Yeah,
Then
so
you just use it forward.
yeah, it just has to find out which task it was and then apply that forward, yeah. That's, and in a very small space, that could be very straightforward. It could be a very low dimensional manifold. Presumably, if you go to real world data or much more complex spaces, then actually the manifold of parameters tells you something interesting about the way in which things vary. presumably, right? But we would actually have to go and show what that looks like and interpret it. I'm not going to go that far in this talk, so please don't hold your breath for that. But on these simple things, this actually can outperform things like support vector machines. So that was kind of a nice result.
Support vector machines were also trained somehow to do all these.
No, the support vector machines are just given the set of 40 points. And then, yeah, so it would be like if I trained a neural network or a linear regression or a tree model or whatever, I give it the training set and I do whatever that algorithm requires me to do on that training set. And then the result of that is I've learned some parameters which parameterize my classifier. So a support vector machine is only, it doesn't know that it's living in the space of Gaussians, basically. And that's why it doesn't have the ability to do as well as a model which is aware of that. But the nice thing here is that I didn't have to know specifically that I was living in the space of Gaussians. I could have been living in the space of natural images or something like that. And the network learns to build those models in a good way.
Okay, so for each task, you can take, if you pick a task, you take 40 samples and then you compare the support vector machine on these 40 with the learned classifier or the recording model.
Yeah, so I take the 40 points, I train a support vector machine, I compare that with the performance of this model in a forward pass and the classification performance of that. Yeah. Okay, so that's, I haven't said anything about communication yet. That's just the infrastructure to put data sets into the network. Now I want to say, well, what about communication? What if now my data set observer is going to be telling other networks about what it found out? So I'm going to use a setup sort of like this, where I have the training set, it goes to a network. There's some kind of message passing system going on where that network exchanges messages with another network. The other network receives the test points. The first network never sees the test points. So the only way for the second network to perform well is if the information necessary to solve the task is somehow encoded in that set of messages. And then for different kinds of message passing, for different kinds of channels, we can ask how is it going to organize that information? What sorts of abstractions show up when it's forced to compress what it learned into a given kind of communication bottleneck? Yeah. Yeah.
Now you're going to show many of these.
Well, I'm going to start with 2. Yeah, so I'm going to start with a teacher and a student kind. So they're not even the same network necessarily. The teacher is the one who gets to see the training data. The student is the one who has to work on the test data. And then I'm going to only allow the one to see the training, the other to see the test and see what happens. And then at the very end of the talk, I'm going to generalize to a population of agents.
Each of the teacher, is it going to be one of those networks?
Yeah, the teacher basically looks like this. So the teacher looks like this, right? And then when the test comes in, this is going to be the student, and I'm going to insert a bottleneck between here and here. So I'm going to say, in order to get from here to here, you have to say talk over a noisy channel, or talk over something with time distortion, or serialize the data, or.
So the teacher has kind of learned this test that classifier or latency representation of this task, or it gets into, you can learn this.
Well, when I go to the message passing, I'm going to have to say how I train the 2. So I don't want to get ahead of myself. So, okay, so actually now I'm going to answer your question. Normally, when you have this kind of communication protocol, the way that people have done it historically is to use things like evolutionary algorithms or reinforcement learning because the communication is taken as a sort of a black box action. You know, you go and knock on the wall, and then the other agent hears something, they don't hear something, light pulse goes, whatever, but it's not part of the agent itself. The communication is somehow this external thing which can't be included in the optimization process directly, so you need these proxy methods. But that assumption, or I guess that frame to think about this is pretty limiting, since actually communication could happen across a differentiable process. I mean, if we care about how these things behave and not how they learn, it shouldn't really matter too much whether or not they actually have a differentiable channel on which to discuss and on which to be trained. And recently, there's this idea of differentiable interagent learning, which is basically that, back propagation across a message passing scheme. It could be a very large number of different message passing schemes. They just have to be differentiable or approximately differentiable. So the big thing here is that the speaker can actually ask, what should I have said to improve your performance? They get this kind of direct feedback, which doesn't exist for people, but it does massively accelerate the training and allow it to scale up to much bigger systems and much more complex tasks than you would be able to do with evolution or even with reinforcement learning. So the main thing that's left has to be, what's the channel? Because if we go down this road of differentiable communication, actually the simplest example of that looks just like another layer of a neural network. We haven't done anything. We just made a small layer. How is that any different than what we already did? That pooling layer was already communicating to the downstream network. So we have to somehow say, well, are we done? Is that it? And one of the things that will happen is that if we make the channel require a certain kind of network or a certain kind of structure to interact with it and to receive messages from it, that's going to influence the kind of representation that takes place. So with our pooling layer, we have this kind of dense distributed representation, which is pretty much standard for what neural networks do to represent things in dense layers. If we make our communication channel only one neuron wide, but we allow the network to communicate over a long period of time, then it has to organize the information temporally. It has to serialize. It has to choose which thing is the most important thing to say first, or how to actually move some kind of internal attention through its memory in order to actually spool out all of the information it wants to communicate into the serial channel. We could also listen with a network that actually receives the entire message and then listens to it at once. So it uses convolution. And in addition, we can put different kinds of noise on the communication. So if the channel has noise in the values, it's going to drive the network to kind of binary encodings, which is a well-known thing. But what if we put things like time distortion noise so that the networks actually can't be synchronized? Then they actually have to somehow have a protocol to get into synchrony so that they can actually interpret the message correctly to make full use of that time dimension. So by putting different structures and different symmetries on the channel, hopefully we can get different ways of thinking about the same information. And so here is what happens when we just do this on a bunch of different kinds of network architectures. So we have a channel, which is 128 utterances long, I guess. And each utterance is just a single scalar value that's between -1 and 1. And there's noise, which means that it actually goes to something very close to ternary. It uses -1 and 1 a lot, and it uses 0 somewhat, and it doesn't use any of the intermediary values very much at all. And that happens across all of the different network architectures we tried. That's just the cost of the noise. We also have a time distortion noise so that the networks can't actually perfectly align sending and receiving. So I can't say the 73rd second of my communication means this and the 74th second of my communication means that. I actually have to encode what things mean by some relative structure, or I lose a lot of bandwidth. And in fact, with the dense network, it can't do that kind of encoding because each point in the message is just seen as a completely unrelated different thing from every other point. So instead, what it does is it just uses very wide pulses. It loses that bandwidth because it can't deal with it. And it's really, I have a better visualization of this. So this is what it looks like during training. And you can see the dense network is very high frequency at the start, but you're starting to see the development of these kind of wide regions. The vertical here is just different tasks. So it's 1,600 different tasks. I've kind of clustered the messages to make similar messages near each other so you can see patterns a bit better. And then horizontal is time. So this is the first thing the network says, second thing, third thing, fourth thing, fifth thing, et cetera, like that. Well, each one of these things is just one task. So each row is completely independent from every other row in execution. But after I've generated the communication, I take all of those messages and then I cluster them so I put similar messages near each other, which presumably puts similar tasks near each other as well.
Okay, but in one row it's just
yeah, that network is doing a forward pass on a single task. Yeah, so the dense network starts very, very high frequency, and then it's going to have to learn to deal with the fact that the indices are not very stable with this kind of channel. The convolutional network, on the other hand, starts pretty blurred out, and the LSTM starts extremely blurred out. And that, yeah?
if you repeat like the first task,
Yeah?
would it be pretty much the same?
Yeah, it would be exactly the same. Yeah, I'm showing you the message before noise is applied. So the receiver would receive something different, but the sender would say the same thing. So as I train them, the convolutional network starts to actually make these pulses shorter. And it doesn't really seem to care where things are in the channel. The dense network pushes all the high frequency stuff to the start and the end, where the effective time distortion noise is minimal, because the networks are synchronized at the start and they're synchronized at the end. But at the middle, there's the maximum deviation of when a message is generated versus when it's received. So it's going to get very blurry here and very, very high frequency here. With the convolutional network, it doesn't have an awareness, or it doesn't really, I guess, need to worry so much about the absolute positioning of things, because it can use relative positioning since it's convolutional. So instead, these stripes end up being much more uniform, and it uses variations in the width of those stripes in order to encode the meaning. And the LSTM is still struggling. Yeah, so by now, the convolutional network has many of these bands. The dense network, you can see it's becoming more uniform in the center. The bands get wider here and thinner there, and the LSTM is still struggling. Yeah, actually, the LSTM does not do well. That was one of the big shocks of this, because you would think, given how LSTMs are very good at handling human-generated languages in a receptive mode, you would think that they would be an ideal architecture for generating language and having communication. But it seems like the bias inherent in the structure of an LSTM as far as generating signals favors these very slow sigmoidal things. And it's only when there's some external source that has a high degree of temporal structure that the LSTM is kind of pushed out of that regime into a more chaotic regime or edge of chaos regime where it's temporally rich. So basically, these things could do well if they were kind of cued that they should be using a lot of high resolution and time structure in order to communicate. But without that cue, they take much longer time to actually find their way there than these other methods. So that actually puts a wrinkle in what we wanted to do, in the sense that the dense network and the convolutional network can't generalize to different length messages very well. The convolutional receiver could, but the convolutional generator can't. So that means that we can't just immediately go to a proper learning algorithm by just giving it more data and giving it more data and giving it more data. With the LSTMs, in principle, we could have, but they're the worst performing of the lot. The other kind of interesting thing here is that, I missed a slide. Oh, well. So there was an OpenAI paper about training agents to communicate with each other in a compositional and grounded way. And what they found is that in general, networks have a tendency towards using kind of coding schemes. So this particular word means this entire meaning, and then this other word means this completely other meaning unrelated to the relationships between the words. So each word is just a kind of index to a list of possible meanings. And if they wanted to get around that, they needed to add this kind of explicit reward for reusing words. In this case, when the dimensionality of the task has gotten a bit higher and the amount of information that needs to be transmitted is a bit higher than it was in the OpenAI task, what we find is that actually we start to get compositionality just because of the high dimensionality of the task. So different parts of this message just vary independently from each other in a meaningful way without having to sort of be coached. So it may suggest that as the dimension grows, the kinds of things that we get from these communicating agents are just going to start looking different. Okay, so we want to go to learning and not just talking, but we have to solve this LSTM problem. And one of the things is this is a very low dimensional channel. So if the LSTM had to produce some kind of chaotic behavior on its own, it doesn't have that many degrees of freedom in which to find it. It also isn't being prompted by any temporally rich input signals. So it has to make it all on its own. And if it starts very far away from the edge of chaos, gradient descent is going to have a hard time finding its way to the edge of chaos. What if, on the other hand, we use the fact that we're doing online learning to actually prompt the LSTM with a temporally rich sequence? Right, that's the hope. So this is the online learning version. And this is very similar to the network before, but now I take data mini batches. I still have to use mini batches in order to actually get good statistics and to get this to actually converge. When I put single data points in with time, it just doesn't work very well. But even mini batches of size 4 work significantly better. So I use the dataset interpreter. I create a representation. I feed that into a recurrent neural network. That recurrent neural network is receiving different independent representations at every point in time. So this operation doesn't know about what was learned here. The evidence is just completely separate, but the recurrent neural network can somehow integrate the subsequent evidence together. That then drives the generation of a set of messages in a lower dimensional space, but not 1D now. It's now 64 dimensional, so it has enough richness for some dynamics. These messages are received by an LSTM. The LSTM generates a kind of cumulative representation, and then that representation goes to the classifier network. That representation is the latent space, the latent representation of the task on which the classifier is conditioned. And in terms of the actual performance, I can compare this blue curve, which is with this communication setup, with the green curve, which is what happens if instead of having a whole communication recurrent neural network here, I just do a running average of the representations. So I just take each of these poolings and just add them together and use that in place of this complicated thing. And the performance is exactly the same, basically. There's this very, very small advantage of the communication there of about 0.01 in the log loss, but it's almost identical. The thing that the communication does better, on the other hand, is, sorry, and this is what the messages look like. So if I have the communication, actually, it just shouts louder and louder and louder. It's actually implementing something like a running average, or very close to running average. So averaging is actually a pretty good online learning algorithm to start with. If I put a sparsity constraint, it talks for a period of time, and now it's temporally rich. It's making as much use of these bits as it can. But then at a certain point, it decides I can't actually gain more by saying anything else than I lose in terms of that sparsity penalization. So it'll actually figure out when to shut up. And this cutoff point will actually vary depending on the data set. And then if I just look at the averaging, I get something like that, which looks kind of like a normalized running average. So it's like, let's say I was doing sampling, and then every time I get evidence for some hypothesis, I add 1 to a bin. And then I want to carry forward how I should treat new evidence of the same scale as the evidence I've had before. Well, if I divide out by n prematurely, then I can do it. Then I get something like this. If I don't divide out by n, if I just carry n along and I just keep track of how many samples of each case I've received, I get something like this where the numbers just keep going up. So in this case, the channel has no upper limit to how loud the signal can be, and the network is not being penalized for using that. So it just uses that. It literally just adds to the previous thing in a completely non-normalized way, and then something downstream is taking care of the normalization.
Okay, so maybe the change in the amount of information that the receiver gets from this should actually change.
I mean, I think we're not really seeing things that are about the amount of information. We're seeing things about sort of computational strategies. So this is one computational strategy for building an online learning algorithm, which is just accumulate in a buffer all of the evidence. This is a strategy which is explicitly being told normalize, do a running average. This is a strategy that emerges from being told, okay, you have to actually only send messages when it's worthwhile. So this thing has nothing to do with the information. There's basically no real bottleneck on it. It can send as much as it wants. This thing is restricted to use the channel efficiently, and so it sends less information. and it has to use this temporally structured code to do so. Okay, so yeah, what's the point of all this? Well, if we look at what happens when we train these networks on a certain amount of data and test them on more data than they've seen during training, what we find is that the running average will improve, but then it saturates. That's the blue curve here. The sparse communications will at first improve up to the point at which we trained it, which is about 30. So during training, they only ever see 30 batches before they restart. And the sparse network can do it up to then, but then it actually gets worse. But the non-sparse network actually continues to improve even when it's received 4 times as much data as it saw during training. So it actually has learned some of that sort of induction or some of that stability to iteration of the learning process.
That's the one that was shouting louder and louder.
That's the one that was shouting louder and louder. It seems really simple, and probably it's almost shouting louder and louder and louder with some very small deviation from that policy, and that small deviation is responsible for the improvement over just the running average strategy. Or some the listening network, the network that actually receives that signal, could also just be doing something more sophisticated by understanding how those things vary.
Do you have any sense of what kind of information is transferred to the channel? It's like, so those two networks already have some shared model.
Yeah.
So the content of the message should be something repetitive, maybe parameters in the models that are shared.
Yeah. Yeah, I mean, that is what is being transmitted, but actually interpreting it, if I did the 2-dimensional one, I could see if I change this part of the message, then the decision surface changes this way or that way. But in the 64-dimensional space, I can't really visualize it. Clearly, when I change the standard deviations of the Gaussians, they'll change the message in response to that. If I change the separation, they'll change the message in response to that. So they are capturing things that you would need to build a classifier. But in terms of a specific figure that would make it very clear to interpret what they're talking about, I don't have one. Actually, I don't, in general, know how to get one.
Must be possible by varying, yeah, basically by varying what they do, the same analysis they do in language games. To see something like a lexicon and a map of grammar, right? But, yeah, you haven't done that.
Well, we tried a few things to do that, but in a much simpler problem where they were just sort of autoencoding, and we could find things like each each bit of the message that they had to transmit corresponded to different aspects of the message that they actually send and things like that. But yeah, it feels like because these things are making a parameterized model, as opposed to making a set of instructions on how to do something, then you still have this kind of coding aspect. You know, one part of the latent space means one thing, one part means another, and you can see relationships between tasks by doing the kind of analogy construction that people do with like the latent spaces of GANs and things like that. But you couldn't like look at the third component in the latent space in the GAN and say, ah, yeah, that one's glasses. It's going to be some arbitrary direction in that space. Whereas with human language, when we tell someone how to do a task, usually we're not saying something like it's task number 573 or the task is separated 1.3 in the first direction and 0.7 in the second direction, but we actually give some kind of procedural instruction, which has a more algorithmic character to it. This kind of network is not going to really do that sort of algorithmic thing. Presumably, if instead of using an LSTM, we were using like a neural Turing machine, it might actually encourage it to transmit tasks using that kind of strategy rather than this kind of strategy. So that's something that would be interesting to do for future work. Okay, so that's communication between pairs. Now what about populations? Because ultimately what we want is to have a society of AIs that work with each other and self-improve, and we can just leave them off for 1,000 years, come back and see what they've done. And in order for that to happen, we need this kind of extensibility in time, this open-endedness in terms of being able to learn more based on more data. But we also need them to have some kind of shared space in which the information comes to be stored. So if I'm learning a neural network, that's the weights, that's the parameters. If I'm learning a population of communicating agents, it's sort of the shared messages and the lore that that population has actually developed, the oral tradition of the neural network population, as it were. So we'd like to start moving that direction, build a population and see what happens. Changing tasks a little bit here, I want something a bit more groundable. The 64-dimensional space has some disadvantages in interpretation. So instead, we're going to use a vision task. And because individuals are not always the same, we're going to take each individual in the population and freeze some aspect of its neural architecture such that it can't change it. So for example, on this vision task, here the network has to classify whether or not the new image belongs to set A or set B. And I can generate a whole bunch of these sets by just making random pattern generating networks. So I might train one agent to build its visual system only looking at a certain pair of artists, or only looking at a certain kind of smaller subset of the total possible set of networks that could generate these images. And if each agent is trained on a different subset of images, their visual systems are just going to be different. They're going to have different filters. The filters are going to favor different things, and then I can freeze them. So I train each agent on its own. They get an input stream of alternating examples of a picture or small batches of pictures that have labels and pictures that don't have labels. When they receive pictures that don't have labels, they have to classify them. Okay. That allows each agent to develop the convolutional part of its brain that takes the image into some kind of latent space representation of the image. I freeze those convolutional parts, then I randomly pair up the agents and have them do the same task offset from each other and exchanging messages. So the first agent gets a training image and the second agent has a test image. The first guy just learns and says something. The second guy fails and says something. They receive each other's message. The first guy gets a test example and has to classify. The second guy gets his first training example, and so on and so on and so on. And I randomly mix up these pairings as I train. So a given agent will over time interact with all of the other agents, but it doesn't necessarily know who it's interacting with. However, they have a message passing scheme, so they could decide to talk about that if they want. They don't. Yeah, yeah. So this is what happens. The really weird thing here is, even though these guys have different visual systems, they still end up saying very similar messages when faced with the same stimulus. So if I actually look at the mean squared error between, or the mean squared difference between the messages that are generated by two different agents given the same circumstances, as I train, that mean squared difference drops monotonically. So these agents are basically coming to some sort of agreement of a shared set of things to talk about that they all have the capacity to perceive well enough to generate the messages accurately. And whether or not that changes what they perceive or what they use to reason, well, it certainly changes what they use to reason, because in the end, these messages are all, in a way, all they have. But the convolutional parts are still completely frozen. So just by post-processing that convolutional output, they actually learn to kind of unify their perceptions and also come up with a shared common language. So that was really surprising. In a way, it's a bit disappointing, because I would like these agents to have to negotiate with each other and describe what it's like to see and things like that. But as expected, the population of agents is not actually changing between or over the course of training. So given enough training, they just memorize each other. Right? It's the whole thing about, do they really need to talk after infinite training? The gradient descent learns everything you need to know about the distribution of agents in the population, and then they just have protocols. But okay.
Probably like go over why for each task the specific set of regularities that are proper to that task wouldn't determine the message.
Hmm?
Why the task, like why the regularities in the task wouldn't determine a certain type of message, like why it's reasoned right there. It might be that this specific set has to be represented very efficiently, like this kind of message.
I mean, I guess I'm not entirely sure I understand the question.
So it might be that even if you vary, you vary your task, right?
Yeah.
And for every type of stimuli, you are going to infer, like produce a message.
Yeah.
And it might be that the regularities are much more tied to the task than you think. And if that's the case.
But the regularities have to be tied to the task. They can. That's the only thing they can be tied to, right?
Yeah, exactly. So because of that, like whatever even if you have more, well, if you come up with if the robot has more sensors and even if I had 5 eyes instead of 2, it might be that I have to represent the same kind of message in order to solve the task.
Well, I think the point is that each network, even if I turned off the communication, they can still perform the task to some degree, right? Because they have their visual system, they have a set of representative tasks that the visual system is trained on, and both networks are actually getting training data. So it's not like the teacher-student case where one is completely isolated from the other, from the data. So just internally, the networks can solve the task to some degree, but they're solving it with a very small number of examples. So it's to their benefit to actually join the information that they've received with the information that the other guys received and basically double their training set size. That makes a big difference. So the messages end up being the only way that they can join the training sets. And it's not very helpful for a blind network to be receiving information about what something looks like, or a deaf network to be receiving information about what something sounds like. So if the only thing that they share is smell, they're going to talk about smell. I mean, it seems like it's something like that, except that rather than being just a simple sensory modality thing, there's a much higher dimensional space of possible variations in their visual system. And that space seems to be big enough that a lot of the idiosyncrasies of the individual agents can be erased by post-processing. You know, it's like if you have a scratch on your eyeball, you can learn to not see it. So there are things like this. there are these random color patterns, and the color patterns are generated by two different random networks. And you have to say which, for a new color pattern, does it belong to set A or set B? So these things have some degree of spatial gradients. They have some assortment of colors. You can find examples of this task in which the colors are more uniform or where the colors are more diverse. So the uniformity or diversity of color can be an indicating feature. So what I can tell you is that if I take a network after training it on the subset and then I test it on something from another agent's subset, the performance is worse than random. So as far as human perception, actually, I find these things really hard to classify personally. I think this would be a very hard task for humans. It's a lot easier for these networks. But the subset of tasks is narrow enough that the network will actually overfit with respect to the global ensemble of tasks, which suggests that they're different. Okay.
Yeah, in a sense, like this task makes even more convincing than another like different classifications. I don't know. Yeah. I can talk loud. But what about the influence of, I don't know, maybe it does rely on the listeners here, because it's a well-mixed population. You do have a different effect on the dynamics. If you had the possibility of having a sparser network of communication between then it would probably produce different results, right? It might be that, yeah, because of non-well mixed would not produce this wouldn't even out the messages. That makes sense.
So I do think that if you went to non-well mixed, it would take a lot longer to even out the messages. I don't know whether or not it would asymptotically fail to even out the messages without some source of noise in the world. Like, I mean, it may just take a million times longer to get there. So if you had a source of noise, on the other hand, I would expect you to get some kind of overall drift of language over time for, say, a linear population that you wouldn't get in a well-mixed population, since the well-mixed is closer to sort of mean field. And in fact, maybe even just an infinitesimal amount of noise would be enough in the linear world. Anyway, these are all easy to try, and the code will be available, so anyone who wants to is welcome to. Okay, so that's it for the concrete results I've got. Hopefully this is a little bit more than a grab bag of results, but now we can talk about what could be done next. So one of the problems that all of these have is that after a certain amount of information, the gain of having another set of information is just really small. It already knows 99% of the information that's available to be known, and so that everything else that it gets is in that 1%, and then the percent of a percent, and so on. And that means that we don't really see open-endedness or a large richness in the communication. We don't see things that spontaneously communicate for long periods of time because the incentives just decay. So the learning is mostly focused on the first data points and the first moments. How do we make it more open-ended? Well, one thing to do is just make the task change. If we go to non-stationarity, then you always have to keep talking to stay ahead of the curve. Your information goes out of date. You have to figure out when the information's out of date, figure out when you should say something new, when you should ask for more information, things like that. It could be a very interesting paradigm for these. I have some non-stationary cases running now. I don't have results ready for the talk, but it does seem like the communication stays richer and it doesn't just shout at the top of its lungs. So something comes out of that. It's also, there's a lot of problems in machine learning where there's a non-stationarity due to the fact that the data is somehow a function of what the network has learned so far. Like in reinforcement learning, if the policy doesn't find very rare things, you don't learn about those very rare things. And then once the policy begins to find them, now the statistics of the problem is completely changed. So if we start using this sort of thing in the non-stationary regime, we'll get learning algorithms that can deal with that kind of situation better than the ones that assume sort of uniform statistics. Another idea is communicating to compute. So this so far has all been about representing information and information exchange. But you could also say, what if there's no question about the information? All of the networks know the same things, but they want to do something with that knowledge. And the thing that they want to do with that knowledge is complicated. So an individual network would take a very long time to do the work, whereas a population of networks would be able to do it much faster. What happens when networks are exchanging messages not to let the other network know about information, which would have this diminishing returns, but instead to enable some parallelization of an algorithm? And we've done a few sort of basic tests of this idea by having two networks here with a channel that has a sparseness penalty on it, and then varying the penalty, we can find a network size in a classification task where when the communication becomes too expensive, suddenly the performance of the set of networks changes abruptly. They collapse. They can't represent these fine sort of undulations of the decision boundary, and the loss jumps up. So this kind of thing going to more complicated problems and understanding what is it exactly that determines the value of computation. So this network is willing to pay a certain number of bits of error in exchange for a certain number of bits of message. But the networks know the same things. So this allows us to sort of go a little bit beyond the information theory perspective, in which it's either whether you know it or not, into something where we can actually start to talk about computational cost in bits. And that may have a lot of interesting implications if we can develop that more. And then another one is looking at these populations and the propagation of information. We could look for the emergence of memes. So these networks send messages. And right now we have a setup where both networks that talk to each other are always being grounded by seeing actual examples of what they're talking about. But what if you had a game of telephone where you have some networks in between that never see any data? They only see messages and they have to generate messages. Then you start to see some messages have the ability to be remembered or to be propagated forward, and other messages get distorted. So you'd have some special messages which are essentially self-replicating objects in that population of agents. And since we know from the evolutionary case that kind of selective filtering is a way to induce the flow of information from the environment into the system, you could have a population of agents that learn by having dynamics in the space of messages that they exchange and the memes that survive or die. Part of this that's also very nice is if we start talking about keeping the information alive in the space of messages, we can start letting the networks themselves decay or die. So that whole going to infinite training time on the gradient descent, imposing a lot of constraints on networks sort of memorizing and assuming things between each other, that goes away. Since now the networks can never train more than 100 or 1,000 or whatever epochs in their lifetime, but the information still has to survive in the population. So that's an interesting area that we're currently doing some simulations on. And then the other thing as well, in this case, we've just gotten compositional language, but nothing grammatical. So the networks index the parameters that parameterize the task out of the ensemble of tasks. They don't give you a set of instructions of how to bake a cake. How could we push the representations more towards that kind of instructionality rather than just being a parameterization? Well, maybe we can use things that actually deal with programming like structures like neural Turing machines as the ear, and then see what that does to the space of messages. And if we can get self-reference, then in a sort of Gödelian way, self-referential communication systems tend to be open-ended. So even if you just start with a couple primitives learned from the data, if those primitives involve the ability to talk about collections of those primitives, then you can always build up these arbitrary statements whose truth value is not accessible in the basic system. The system can essentially self-extend. It can find new questions that have to be answered for it to move on. And if there's an actual trainable neural network equivalent of that idea, that would be a really promising place to look for a kind of open-endedness. And that's it. Thank you. So Martin asked if I could repeat the point about generating questions. And the idea is that in a system in which each sort of each symbol or each utterance has a meaning which is not referential in nature, which doesn't rely on the content or doesn't exploit the context to be interpreted, let's say, then basically the set of things I can express is bounded just by the set of things that I've made symbols for. If I have reference, I can construct things to talk about out of sets of those symbols that are now distinguishable from the symbols themselves. So if I have like A and B and a way to talk about A, B as being separate than just A and B, then I can talk about talking about A and B and talking about A and B and things like that. It may not be a very interesting open-ended hierarchy to build, but at least just through that kind of induction that we're trying to get to develop in these models, it leads you to the ability to express more complex things than you were trained on. So whether that ability manifests as something useful or something that we could actually do something with is a really open question that we'd have to explore.
Once you learn some kind of combinator function operation, combine things, make a new thing out of
Well,
things, then
it's more than that, because you also need the ability to distinguish the combination from some other symbol in the same space. So if I combine A and B and I get C, and then maybe I have a group or something like that, and I just continue to cycle around in that group, that's not going to do it. But if the combination of A and B is not the same as combining A and B, like if I can say this is A and B and this is the combination of A and B, then I can kind of do it. I don't know. So the way that it's constructed, well, so the way that it's constructed in the kind of Gödelian proof is that you take every statement and you give it a number, and then you basically find that when you can make statements about statements, then that set of numbers is uncountable. There's probably actually a little bit more to the proof than that. That was really too ad hoc. But
I kind of see the. I think I get the idea. It's very interesting. This is a way of communication, but I think of communication. I think about something like agent A and B share some same representation outside, and the agent A tells agent B what it is looking to see. So this is a kind of symbolic symbologram. Agent A has some little representation of some symbol.
Well, there's a lot of work done on the symbol grounding problem, which is what I think that you're kind of referring to, where you have an ambiguity in how you would refer to things that are concrete on either side, and then there's a negotiation to finding shared representations. But beyond the sort of symbol grounding level of things, there's also sort of manipulative language. So this is the whole Wittgenstein flipping from one point of view to the other halfway through his life thing, where at first there was the argument that language was primarily about things that were grounded in reality, so that when you were talking about something, you were actually talking about a thing that existed. And then another point of view emerged from the same guy, basically, that actually language could just be purely about the behavior that it induces in the listener. So I would say something only to get someone else to do something, and it doesn't have to be about something concrete. The interesting thing, well, I think there's space for both. And actually, you need a lot of richness to get between the sort of simple animal communication and our ability to have a talk.
I just wanted to make sure this is on top of symbol grounding. So this looks like something like a formal sentiment.
I would say like this result is an example of symbol grounding, right? Because here, when shown the same stimulus, the different agents with different visual systems say the same thing. So they've clearly come up with some kind of naming system. But this one is probably not an example of symbol grounding, because here the communication purely facilitates solving this abstract computation. So in a way, because these things are trained to just succeed at what they're being asked to do, different kinds of tasks induce different kinds of structure, and informatic tasks seem to induce a grounding, whereas computational tasks may induce something very different.
The grounding is still there, but it might be,
The grounding might still be there, but it's kind of hardly wired into the task that you define, right? You're playing a game like the Wittgensteinian game of doing something, and through this, the game is actually equal to the universe you create with the structure and rules, right? So you are still playing this game in the same sense that you are playing a game with bacteria and cells, like coming out, emerging from nothing in the universe. So there's no clear separation.
I mean, maybe another way to put it is that the move to abstraction is that the agents start to create things internal or shared between them to ground symbols that you can't find simply by looking in their environment anymore.
Are you planning to test these with some good examples? Or you would expect to have
Sorry, yeah.
different accuracies? I mean, let's say if you train all agents separately, I'm a bit far away. If you train all agents separately and you average their accuracy and the ensemble, would you expect these to outperform?
They do. Not by much. Yeah, so when the agents cooperate, they do outperform the agents alone, but not by very much. The additional gain is really, it suffers from diminishing returns. Do I have the curve? Maybe I have it somewhere. Give me a sec.
So there are experiments. I'm not sure how much they replicate these things, but there are experiments in which they ask, they go to a stadium, and they ask people that go by, tell me how much this object weighs. And usually the average of all these people say it is, it's better than the best estimate each single.
Yeah, I mean that's even before the communication stuff, right? If I look at where this result, right? So here, even this averaging guy is doing that. He's sort of self-ensembling. I mean, in a very simple way, because his biases are the same for every data, every block of data that he receives. He does have the same weights that parse it, so you don't have this kind of reduction of bias through having variations in the training and things like that. But you are still averaging in order to get a better estimate, and that's just including more information about the task. With the communication, that process is made a bit more efficient by doing something more sophisticated than averaging, slightly more sophisticated than averaging, because it still actually mostly does averaging. So I mean, in that sense, it's just sort of a bit counting, right? It's if you have 10 examples, there aren't that many bits that you can get. If you have 100 examples, you have that many more bits. I think the trickier thing would be in a case where when you go to the crowd, everyone still has the same examples, but each agent processes the examples differently, and then they communicate. So like, let's say I take my pool of agents that have different visual systems. I take all of these guys and I show them the same pictures and ask, will they still send messages despite the fact that they all have the same bits coming in? And I would expect that, yeah, they would still exchange messages and improve the performance a little bit above what they would do alone. Because they are each individually overfit, right? So they're each individually not performing. They have a bias. And then by combining those messages, they actually dilute that bias. But we'd have to go and try it. Yeah.
Yeah. So yeah, you started with this a setup of meta-learning. But how essential is it to have meta-learning to establish this kind of communication? So maybe like in most cases, like in human communication, we just transmit the contents of what we see or what we hear. But with this meta-learning, the networks are probably telling the other network that how they should classify new set of images and so on. So, but why did you make this design?
So the differentiable communication can be used for more than just meta-learning. You don't need meta-learning to use that technique. And a lot of the papers that work on that are using it for other things like coordination games. It's pretty general in that sense. The meta-learning thing struck me as the place where this sort of thing had the most practical value, in a way that the way we actually did this research is we said, basically, hey, wouldn't it be neat if networks talked to each other about stuff? Or wouldn't it be neat if they had phenomenology and talked about what it's like to see or what it's like to hear or what is blue? How do we get that to happen? And we tried a bunch of things and got a lot of stuff to happen, a lot of the results which I've shown in this talk. But then at the end of that, a lot of it sort of, once we understood what was going on, it looked very similar to what we could already do without communication. So when I took all of those results and tried to say, what is it about this that's really unique? Or what is it that the communication is enabling that we wouldn't have seen in a case where we didn't have multiple agents, where we didn't have these kinds of things? The thing that seemed to pop out to me was that when these agents are learning to integrate messages with experience, that is actually a learning algorithm. And being able to actually do meta-learning in this way seemed very promising to kind of get to the next sort of post-gradient descent class of learning algorithms. It would, historically, AI spent a lot of time trying to do everything symbolically. And that wasn't very successful when we just tried to do it by hand, when we tried to write sort of symbolic AI the way we would just imagine things should work. Going to this kind of optimization perspective, things are a lot more successful and they don't have as many human biases in what happens. So they find solutions, whatever those solutions may be, good or bad, from our aesthetic point of view. Part of the idea was that maybe by letting an AI try to make the jump to symbolic, you would actually have something more successful than when we sort of take our point of view embedded in human experience to externally construct something symbolic. This isn't symbolic yet, of course. I guess the point is that for a long time, sort of symbolic cognition was taken to be what AI was obviously how it was going to work. We, as humans, kind of pride ourselves on our rationality and our ability to do logical reasoning and things like that, and that naturally lends itself to this symbolic view of cognition. Then it turned out that when you tried to build that by hand, you get these really Baroque structures where it has a bunch of rules that are handcrafted and the thing is not very extensible. It doesn't adapt itself on its own. You have to build it for each circumstance. It's not very robust. It has all of these problems. So AI working along those lines kind of petered out a bit in the first kind of AI winter. And then recently, these non-symbolic approaches have been extremely successful because you don't tell them how you want them to do something. You tell them what you want them to do, and then they figure out how to do it. So in this case, it gives us the opportunity to say, well, what if we ask it, how would you do a symbolic AI? And then that might be able to actually come up with things that don't suffer from the kinds of preconceptions that we have about our own cognition.
Cheating a bit, right? This is still symbolic. It's just a different type of symbolic.
No, I don't. It's not at all symbolic in the ways that symbolic is meaningful as a distinction.
I just define what I mean by symbolic then. So it does, you have maps of different sets of weights that would correspond to how you solve tasks. So if you call that, well, you can call that rounding a symbol, then this is a different symbol than just having a one-to-one mapping in a vocabulary, for example. It's not a lexicon, but it's a mapping that helps you solve tasks, right? Problems.
I mean, I guess I just disagree on the definition of symbolic then. The kind of symbolic that is meant in symbolic AI and the kind of AI, like the GoFi style of thing, wasn't what you're talking about, but it was rather like propositional logic, things where you have combinator rules. And then those rules would constrain the kinds of statements that could be expressed in the system, and you would use that structure in order to actually perform cognition. And I would say all of that kind of constraint-based thing is very different than modern kind of neural network style AI.
Yeah, so good. Now I agree. And now this leads to a question I had. Then, if this flow of symbols between agents, and it doesn't matter to me, like if it's between agents or not, if this is the stuff that we want to understand in neural networks, in order to understand how they really work or can work better, is there a good paradigm shift that can be done by essentially considering that everything in neural networks is communication, and that you can propagate errors as information flows within those networks, in the same sense that you analyze how you can form grammars, message passing between agents. Yeah, short version like this, but I know you have things to say.
I mean, I guess the thing that doing this makes me realize is that even if you have communication, and even if the communication becomes grounded in the sense that you solve something like a symbol grounding problem, it doesn't mean, that does not seem to actually be the thing that distinguishes the sort of symbolic reasoning. So, you know, there's, if you use a LSTM, it has an attention in the sense that it has gating. And if you have a very big LSTM, it can have memory. It could memorize things, memorize inputs, store things, things like that. But the fact that it's kind of using these dense updates, that everything is mapped to everything, structures the kind of computation that an LSTM does in a way that's different than a neural Turing machine. So if you look at the generalization properties of an LSTM on, say, adding two binary strings together, and a neural Turing machine on adding two binary strings together, the generalization to different sequence lengths is much stronger in the neural Turing machine than the LSTM. And where am I going with this? Well, the point is that in the neural Turing machine, there's a kind of a sparseness of what can change from moment to moment. So every operation that the neural Turing machine does, every cycle of the recurrence, is specific in some way. It only refers to this small bundle of memory sites or this small bundle of values. And the LSTM is not specific in that fashion. That, to me, seems to be the most promising place to look for the emergent, the kinds of propositional structures in symbolic logic. And I think it's borne out by the benchmarks on networks that do symbolic logic. I think the neural Turing machines actually can solve things like the Babel tasks. And,
Yeah, thank you
all
very
right,
much.
thank you.
Maybe we can continue this, but maybe we can just close this video.
Yeah.
We can talk at it after.
Yeah. Wow.
I like the loop, by the way, in the talk, like start with death and we end it with death.
Well, you just like death.